In the next subsection, I want to look at longest common extensions as one application of suffix trees and an additional building block that allows you to solve even more problems based on suffix trees. I'll tell you first what these longest common extensions are, and then we'll look at one example where that allows you to do a more interesting algorithm than without them. Longest common extensions, again, have a text as input. And then at query time, so as always for data structure problems, I give you the text up front. You can do your magic on the text up front and take notes. You can build a data structure from it. And then later I'll ask you LCE queries, longest common extension queries, which consist of two positions, I and j, in the text. And you have to tell me how many characters can I read from these positions so that what I read is the same string. How long can I extend the same string from these two positions? That's an LCE query. So formally expressed here, it's the maximal L so that Ti up to Ti plus L matches Tj up to Tj plus L. And here I and j are given. It's quite similar to longest repeated substring in a way. But here we're given the two positions. So you're asking, what's the longest repetition at this particular point? Right. It's a relatively easy thing to do if you don't care about the running time. So maybe the trivial solution as often is don't do anything at pre-processing time and always compute it from scratch at query time. So I call this the store nothing solution. Probably deserves quotes. And then how do you solve an LCE query? Well, you have two pointers, and now you just compare character by character as long as they match. This is similar to what we did in the naive string matching algorithm, so I don't want to spell out some pseudocode for that. But it's clear that you walk along this longest common extension, and the longest common extension could be long in the worst case. Imagine, worst case, stupid one again. You could have a text that consists of all A's, so no matter where you start, you'll always run to the end. And so the worst case time of an LCE query is linear. And that's fairly slow. It's not very interesting to use the LCE query then, because you could have just done that from scratch. What we'll find is with some pre-processing on the text, you can get much faster. All right? Now the N really here is the L, the output, which is sometimes useful to know. If you can guarantee that the longest common extensions aren't long, then maybe this store nothing approach is good enough. It's the chapter about suffix trees, right? So maybe not a big shock that we can use suffix trees to do that a little smarter. If we have the suffix tree of this text T, the longest common extension between positions I and j, say we do LCE of 1 and 3, is finding the two leaves that correspond to that. Okay, I picked a boring example. Anyways, we can do another one. The longest common extension is nothing else than the longest common prefix of the suffixes starting at these positions. Complicated way to say something simple. So here's the text, positions I and j, and I ask how much can I read at these positions so that this matches. Another way to say that is I look at the suffix starting at I and the suffix starting at j, if I align those. So this starts at I, goes up to n, this starts at j, goes up to n. Then I want these to match. And so it's the longest common prefix, the longest joined part that these two have in common. And remember, we wrote ti, tj for the suffix starting at that position. So that's just a different name for the same thing. And the longest common prefix of two suffixes, that's the, if we go to these two, we notice that they share a path for a while and then they diverge. So the part that they share is exactly the path up to this node where the two split. And this node is called the lowest common ancestor of the two leaves, just in the genealogy tree meaning. You walk up from the two until you, for the first time, join paths. And such a node always exists, and it has some label from the root down there. That's your longest common extension. So in this case, LCE of 1, 3 is the number 3, because LCE asks for the length of that string. We can do one more, just to show that sometimes these are boring. I can ask for 6 and 4. So if I go to these two, here's 4, here's 6. They have nothing in common. The longest common ancestor exists, but it's the root. And so in this case, LCE is 0. Okay? Okay, I put this down in short notation and put a box around it because that's something useful to memorize. It sounds a bit cryptic, but if you keep the picture in mind, you can actually rederive it. So longest common extension is nothing else than finding lowest common ancestors of leaves in the suffix tree. And then you need your string depth, which is something used before. Now, if we do this in the suffix tree, we have only pushed the problem one step further. We now have to find lowest common ancestors instead of just walking along the tree, the string. It's not so clear if that's any better. What we could do is we could walk from the leaves upwards step by step until we find a common path. That's possible, but it's actually not any faster in the worst case. You can create suffix trees that are very deep. And still, if you have two leaves that share essentially no common prefix, you may have to walk up a linearly long path. So that translation to the suffix tree didn't really help us in that case. Of course, there's another trivial solution. We could pre-compute everything for LCE, store all the combinations of I and j in a big table. That's all right for query time. You can just look it up then. But the space and pre-processing time are prohibitive. So these two simple solutions won't get us any further. And here's another black box that will only come back at the very end of this module. For now, you have to just take it as another magic trick. You can pre-process the suffix tree in linear time. So essentially, again, the time you need to read the string or read the tree, so that we can find lowest common ancestors in constant time afterwards. No matter which two leaves you pick, in one step you can jump to the right node. These are literally copied from what I said about the suffix tree construction. And they build up on a few nifty tricks. It wasn't so clear how to do it before people showed it, but now it's something you can teach in a module like this. It's not the most ugly data structure. And it's definitely useful in practice. It's not hard to implement. So this will be the topic of Unit 9, which I labeled as outside of the exam because it's just a little too much for an introductory course like this for some of you. But I wanted to show it because I think many of you will enjoy it. It's a lovely topic. It's just a little technical at a few bits, so I don't feel it's useful on an exam. But I think it's good to show you a little beyond the textbook level. So we'll come back to that. That's a promise, not a threat. We'll crack this black box open too, but I have to ask for a little more patience in this case. Right. For the moment, let's close the box and just use this as a result. We can find lowest common ancestors in constant time after spending some pre-processing on the suffix tree. And it builds on the suffix tree, so that will be hidden inside. In a way, we've already nested two of these black boxes, one in the other. But that's the part for the moment. So given a string, you can look at it in linear time, and afterwards you can say, for any two positions, how far can I jump where the characters match. Now, if you see this for the first time, the definition might be a bit overwhelming and slightly weird. There's a very not straightforward application of this, where I hope this makes it clear that this can be a useful primitive. This is, for the first time, a problem where we look for inapproximate matches. So we're back to string matching, not necessarily offline, although we'll treat it as such. You're given a long text, and you're a shorter pattern, but could still be a few thousand characters. And you're trying to find a position where this occurs in the text almost without any mismatches. To make this more precise, what we mean by that, we fix a parameter k. That's the number of errors you allow. And then we look at a match where the Hamming distance between the positions in the text and the pattern is below k. So I have to tell you what the Hamming distance is. And it's just the number of mismatches between two strings. So if you have two strings of the same length, you have maybe many characters that are the same. And then maybe a few positions where they're not the same. So if you have three positions where the characters are not the same, Hamming distance would be 3. You just count how many mismatches there are. And there's no ambiguity, because we assume this is only applicable if the strings have the same length. So there's no leeway in choosing what to align to what. All right. If you take the definition as such, you can easily adapt our brute force string matching algorithm back from Unit 4 to count the number of mismatches. Remember, at the time we said, okay, every position in the text is a guess. Let's try to find how many characters can I align between the text and the pattern. And as soon as I had one mismatch, I said, no match, next. I'm trying the next guess. Instead, I can replace this inner loop with one that just counts how often I have a mismatch. And when the number at the end comes out smaller than k, I return, here's an approximate match with so many mismatches. And otherwise, I continue. So the time we're comparing this against is this brute force string matching time, n times m. May or may not be good enough, but if m can be fairly large, it might not be good enough. And we can definitely do better using our new fancy toy, the longest common extension. Similar to what we did with generalized suffix trees, you can apply the same trick for the longest common extensions. If you look at a text that consists of, well, T and P with some markers in between, we can build the LCE data structure on this text. And then if we ask a question, what's the longest common extension between this position in T and this position in P, I can get the answer of how much I jump and at these positions. Even though I'm looking at two different strings, if you make them part of one big string, it's actually just the special case of this longest common extension. So, I mean, to not have a slide where I didn't scribble something on, let's put our construction here. So that's the text and the pattern. And if I happen to ask a query where I is here and J is there, I can find longest common extensions between the two strings, but I'm really just using two positions in a long string that's constructed in that way. So all the black boxes from the previous slides can be used. Okay, I slightly looked into the box. We remember that we're building this on a suffix tree, but we can use the generalized suffix tree. And then lowest common ancestors work in this generalized tree just as if it was a normal one. Still with me? So how would we want to use this to speed up the K mismatch matching problem? Well, intuitive idea, let's use the brute force algorithm, but whenever we have something to check, we first jump over all equal characters. Maybe that brings us a lot of positions to the right, and we don't have to check, oh, matches, 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 matches meticulously all the time. Instead, we just jump. That's pretty much what we'll do. That will be called the Kangaroo algorithm. Let's do this to make sure you're with me here. Not that this is a hard one. I forgot to start the attendance code. It's not supposed to be a trick question. Can you de-stick out the emoji numbers? All right, you're not seeing this yet. Well, either way, so Hamming distance is the number of characters that do not match if you just write the two strings on top of each other. I did that here. And okay, apart from the handwriting, E is the same, A is the same, R is the same, but the other two are not. So the Hamming distance is 2.
How is Hamming distance defined if the strings are not equal length?
If the strings are not the same length, Hamming distance is not defined. Doesn't make sense in that case. There are other metrics. The edit distance is a well-known one, where you say, I can take one string and now I can edit it into the other string by replacing a character, inserting a character, or deleting a character. And you say, what's the minimal number of such operations that takes me from one to another string? That's more general, but it's a little trickier to do string matching with that. All right, let me show the attendance code again for those who came late. And we can move on with this one. So Hamming distance is 2 in this case because 2 characters are not the same. Goody. The algorithm that exploits the LCE data structure is called the Kangaroo algorithm because of these jumps we always make. And it works like this. We have one loop over the positions in the text, similar to the brute force string matching algorithm. Then we have a variable that counts how many mismatches we have seen so far. And we have a position in the text and in the pattern. But now instead of doing single comparisons, we first jump over all the equal characters between the current position in the text and the pattern. So again, if we're currently at position I in the text, we imagine we put the pattern below this. And then there's a certain number, say, of characters that are equal. And so the first step brings us right behind this. So we jump from I to this new position, I plus L. Now, if we have jumped L positions from the LCE data structure, it means we could not jump L+1 positions. Otherwise, it would have done it. So without doing another comparison, we actually know there's always this mismatch here between the next characters. It has to be like that, otherwise we would have jumped further. So we don't actually have to do this comparison, but we know there's a mismatch, and we can advance where we are in T and in P by both L+1. And so we're looking at the next position. And from there, again, we do a jump. How many characters are equal? Well, who knows, but maybe a lot. And we jump from here to that position. And then again have one more mismatch. Now, at some point, we run out of pattern with this procedure, or we run out of mismatch budget. If the mismatches go above k, then we stop, because then we needed too many mismatches for this to count as a match. And if we run out of pattern, then we return a match at this point. And we could have returned the number of mismatches at this, but the formulation of the problem asked only for the index. Easy to change. How well does this work? The pre-processing n plus m, that comes from the LCE data structure. That's linear in the length of the string, but we have to take the text and the pattern. And the matching part, the algorithm above it, that is now, instead of n times m, where m could be in the thousands, it's n times k, where you tell the algorithm how many mismatches you still count as okay. It's probably a few, right? If you start getting into several dozen mismatches, it's probably no longer recognizable as a match. So the assumption is that k is substantially smaller than m, otherwise the thing is not very interesting. So we get some decent speed up, at least in many situations, when k is not too small, not too big. All right? The algorithm above is not that hard. It uses this nice black box to do these jumps. And without that, it wouldn't work. Again, just for your curiosity, people have thought about this problem much more deeply. And you can get much faster with more complicated algorithms where you can essentially divide by m. So you can do something almost like the good cases of Boyer-Moore, where remember, if we were lucky, we didn't have to compare all the characters. A few characters per guess could have been enough to decide there's not a match, and so you can jump further. Something similar can be done here, but not quite as efficient. What I mentioned before, edit distance as a generalization, when you allow insertions and deletions, which is a bit more realistic if this is searching with typos. That's possible, but it's a bit more tricky, so beyond the scope for today. As a last application, very briefly, not too interesting, but can be useful. Not interesting from the theoretical side, but can be useful. We can allow in our pattern to have wildcard characters, so a don't care character. So it's not the Unix shell star which matches any string. It's the star in the sense of, I don't know, a dot in a regular expression. So where would we use a star? There was some, you guys remember? Well, I mean, the definition of star here is any character, but a single one.
Import star we do in Python library. Like to import all the libraries.
Yeah, so okay, that's true.
What are they? Pretty much. Yeah, it's also using SQL as character. Zero or any character.
Yeah, that's my point. So it's often used. So Python import star from and so on, and SQL. But there, the star can be any number of characters. What I mean here is a single character. I just don't care which one. I didn't want to use the dot because that's hard to see. So a single character is the important part. And so then it's pretty much the same as asking for matches with string matching with up to k mismatches, where just the wildcard always counts as a mismatch in that sense. So you can adapt the algorithm from before to this. That was the application number 6, and for now the last one that I want to discuss. But just to drive that point home, there's a whole range more that, for example, Dan Gusfield collected in his book, which is it's a bit of the suffix tree Bible, if you want. Has all sorts of things that you may or not want to know, may or may not want to know about suffix trees. Any questions on the suffix tree applications? I want to segue into the next part a bit by discussing, zooming out a bit from what we've seen, discussing what suffix trees are good for. I mean, I showed this longest common substring problem several times, where I was conjectured not to be possible. Pardon?
Why did it take so long to invent suffix?
Oh, why did it take so long to invent suffix trees?
I heard that,
Yeah.
Talk was so many before.
I think the answer to that is read the old papers about the suffix tree construction. So the definition of suffix trees is not so hard to come up with, but to construct them in linear time is a little tricky. And I mean, it could have been possible in principle that you could define this nice data structure. It's just not possible to compute it quickly, and so it's no use. I think that's the reason. Now, in hindsight, it's always hard to say what was the trickiest bit. I'll show you a construction, which is the modern way to do it, which is much, much cleaner. So maybe after that, you can ask the question again, or ask yourself the question again. So it took a while to get them, but then once they're here, they're linear time, linear space, and allowed all sorts of problems to be solved in optimal time. But they have some downsides. Some parts that we didn't talk about is how to represent them in detail in memory. I didn't show this yet, but you will see that there's some overhead to doing it with the suffix tree. It gets a bit complicated. The last part is something I want to discuss a bit. How do you store a trie? Well, it's a tree, so we need some way to represent nodes, and then it has children. So one obvious way would be every node has an array of child pointers for all the possible alphabet symbols. That's all right if you have a handful of alphabet symbols. If you have many more, think again of the Unicode character set, 150,000 or something. You don't want every node to have 150,000 pointers, almost all of which will be null or empty. That's not really efficient. So another option would be give each little node a small data structure that holds the child pointers. For example, it could be just a linked list, sorted in alphabetic order. That's much more space efficient, but now if you have one node that has gazillions of children, could happen sometimes, it's quite slow to navigate. So all what we discussed assumes that you can jump in constant time from a node to its child with a given character. That's not possible anymore if you do this linked list. Now you can go slightly more sophisticated and do a little binary search tree in each node, or you can employ some hashing tricks. You can try to work around your way around this fact that most nodes will have very few children, but some nodes may have a lot of children, and we want fast navigation. But it seems either way, you at some point have to pay, either in time or in space, and often in both. It's not completely for free. You can do a fairly decent implementation, but you still need a handful of pointers for each node at least. And so this the number of pointers per node, this constant in the linear space, can be much bigger than the actual text. If the text barely fits in main memory, as for a human genome, say, that's a bit of a problem.